Welcome to demonstration 2 of FPGA-based signal processing systems. In this demonstration session, we would be demonstrating the simulation of sequential circuits that were taught in the lectures. So, the first example that I'm going to take is of a D flip-flop, asynchronous D flip-flop. There it is. I have the code written here already, so I will be explaining it how to simulate. This is the source code for asynchronous D flip-flop, and this is the test bench and source code. So in asynchronous D flip-flop, we have input D, that is data, input clock and reset. Outputs are Q and Qn. Q and Qn would be defined as reg. Then in an always block, we would have both positive edge of clock and positive edge of reset. Because it is asynchronous, we will be having this reset signal also, positive edge of reset also in the sensitivity list. If reset is 1, Q will be set to 1 bit 0 and Q1 to 1 bit 1. Else, it will execute this begin end block, that is output. Q which is output would be equal to D that is data, and Qn would be not of D. In the test bench module, this is the module name of test bench. Inputs are declared as reg, which are D, that is data, clock and reset. Output is Q and Qn, they are declared as wires. Then we will instantiate the unit under test. Unit under test is the module name, which is a DFFR. So it got mapped and thus we instantiated it. Then initial begin, we will put display and monitor commands. All the variables that we want to monitor would be listed out here along with time. Then we would initialize inputs. The data is 0 at time equal to 0, data is 0, clock 0, reset 0. Then we will wait for 100 nanoseconds for global reset to finish. Then we will end this begin block. Begin end is ended here, and then we will put the stimulus here. Put a stimulus, and along with it, one clock also needs to be generated because it is sequential circuit. So always block is used to generate a clock. This clock is of 200 nanosecond time period. Then initial begin, we will provide the stimulus here, like after 50 nanosecond, reset is made 1 bit 1. Again after 50 nanosecond, reset is made 1 bit 0. And then data input is 1 bit 1. Again after 70 nanosecond, reset is equal to 1 bit 0 and data is made 1 bit 0. So on up to this point, that is 170 nanosecond. After 170 nanosecond from this simulation time, reset is equal to 1 bit 0 and data is equal to 1 bit 1. Then we will end this begin block and end the module. Then we will run simulation here. So this is the waveform editor window. Here all the variables are listed out here. D is data input, clock is the clock signal, reset, RST is reset, Q and Qn are the outputs. These values are the last instant of the simulation time. And this is the waveform. Here we can see that when reset is equal to 1, here our output becomes equal to 0 as given in the code. Then when clock is high and data input is 1, then output becomes equal to 1. After that, up to here, at this point, clock is again high, and when clock is high, it is found that data is 0. So at this rising edge of clock, our output also becomes 0, and likewise, it proceeds up to the end of simulation time. So this is the working of asynchronous D flip-flop. Now we will move on to the next example, which is of a toggle flip-flop using instantiation of a D flip-flop. This is the source code for toggle T flip-flop. Inputs T that is data. Other inputs are clock and reset. Output is Q and Qn. Then a wire is defined as dt. Then this dt is assigned the value of Q XORed with T. Q is the output of the instantiated D flip-flop. This DFFAR is a asynchronous D flip-flop that we demonstrated in the previous example. Its output Q is when XORed with the input to the T flip-flop, it gives a value that is assigned to dt. Dt is a wire, and this way this toggle flip-flop is design is done using instantiation of this D flip-flop that we have demonstrated in the previous example of this session. Then we will come to the test bench. Its module module name is TFFTV. Inputs are T, clock and reset. They are defined as reg. Output is Q and Qn. Q and Qn, they are defined as wire. Then we instantiate it. Module name is TFF. UUT is the unit under test. TFF is the module name of this toggle flip-flop. Then initial begin, we will initialize inputs T equal to 0, clock 0, reset 0. We will wait for 100 nanosecond for global reset to finish. We'll end this begin block, begin end is closed. Then we will add stimulus here again with an initial command because we have to monitor it from the beginning from simulation time equal to 0. So monitor time and all the variables would be listed here that we are going to monitor. And the stimulus after 10 nanosecond, hashtag 10, that is 10 nanosecond, reset equal to 0. Then again after 10 nanosecond, clock equal to 1, then T equal to 1, likewise up to this point. Then we will end it, and all we need, as it is a sequential circuit, because we have clock inputs here, we need to define a clock also in the test bench. So using an always block, we have defined a clock of time period equal to 100 nanosecond. Then we will end this module and run the simulation. In the waveform window, here T is the input, clock is the clock signal, reset signal, Q and Qn are the output. So we can see here that when reset is high at this point, and Q output becomes equal to 0. And again, when reset becomes low, that is 0, it again and then at the positive edge of clock, the output rises to 1. After that, since T is 1 continuously, that is input data is at continuously high 1, the output keeps toggling between 1 and 0, 1 and 0. It keeps toggling because this T input is continuously high. So at every rising edge of the clock, our Q output of toggle flip-flop toggles. It is Q toggles at every rising edge of the clock after that. So this is the simulation for toggle flip-flop. Then we will move on to the next example, that is a counter, that is mod 4 counter using instantiation of this toggle flip-flop. Here you can see that this toggle flip-flop source file is already added here. Thus, we are able to instantiate it directly here. So the basic codes means the original codes I have commented out here because we don't need them. We have added them as source codes here. TFF is here, toggle flip-flop. And this instantiation, and for mod 4 counter, what we do, input is a clock, a reset, output is AQ and AQN. Two wires are defined, T and DT0 and DT1. Instantiation of toggle flip-flop is done. This TFF we already demonstrated in the previous example. Then DT1, two wires are there, DT0 and DT1. DT0 is assigned value of 1 bit to 1 continuously, and DT1 is assigned AQ naught and ANDed with DT0. DT0 is 1 bit 1 continuously, and AQ0 is output of the first toggle flip-flop, the toggle flip-flop that we instantiated and is named T0. So this AQ0 is coming as an output from this T0 toggle flip-flop. Toggle flip-flop file is source file is already added here, instantiated. So it is ANDed with DT0, and this output that is obtained at DT1 wire comes as an input to toggle flip-flop 2, and it gives an output AQ1. So basically we have these outputs from the toggle mod 4 counter, which are AQ1 as MSB and AQ0 as LSB. And then we will move on to the test bench. Here is the test bench. Module name is mod 4 counter TB. TB is test bench. Inputs clock and reset defined as reg. Outputs are AQ, a 2-bit output AQ and AQN. These are 2-bit outputs. They are defined as wire. Then we will instantiate the unit UUT, that is unit under test. Mod 4 is the module name that we have given here, mod 4. So mod 4 is instantiated. So instantiation is done. Now initial begin means we will initialize the inputs, clock equal to 0, reset equal to 0. Wait for 100 nanosecond. We will give a time of 100 nanosecond for global reset to finish. Then we will put a stimulus here. Initial means we will put an initial block again, because we want to start the stimulus from simulation time 0, as well as this monitoring has to be done from simulation time 0. All the variables are listed out here along with time, clock, reset, AQ, AQN that we want to monitor. Then stimulus is after 10 nanosecond from simulation time 0, reset will be made 0. Then again after 10 nanosecond, that is it means after 20 nanosecond from time equal to 0, clock will be made 1. Again after 10 nanosecond, that means after 30 nanosecond from time 0, reset will be 1. So on, it will go up to here. Then we will end this block, and using an always block, we will be defining a clock which is of 100 nanosecond time period clock. As it is a sequential circuit and it has a clock input also, we need to define a clock using an always block. And then we will end the module. There is the output. We will fit it to the window. These are the variables. Clock and reset are the inputs. AQ, AQ0, AQN are the outputs of toggle flip-flop. And these are the 4 different states. It's a mod 4 counter. It will have 4 different states: 0, 0, 0, 1, 1, 0, and 1, 1. And again, it keeps repeating at every positive edge of clock. This the mod 4 counter jumps to the next state. Again, at the positive edge of clock, it jumps to the next state, and so on. And when reset is high here, it is when reset is high as defined here, it will according to the asynchronous D flip-flop, it will respond accordingly, means as it was defined there. So this is the simulation for mod 4 counter. Then we will move on to the next example, which is a mod 64 counter. It will use instantiation of this mod 4 counter, and this mod 4 counter had used an instantiation of toggle flip-flop, which had used an instantiation of D flip-flop, asynchronous D flip-flops. So this mod 64 counter. We have the code here. So it is updating. We have the previous modules defined already. We can directly instantiate it like this. No need to write all the modules here once again. It is directly instantiated using this mod 4. Mod 4 was the module name for mod 4 counter. So for mod 64 counter, input is clock and reset. Output is a 6-bit output, AQ and AQN. In mod 4 counter, clock and reset, we need 3 instantiations of the mod 4 counter, and each such mod 4 counter is and the names of those 3 mod 4 counters are M1, M2, and M3 as instantiated here. Input is the same. Input is clock and reset, and output from mod 1 from M1, that is the first mod 4 counter, is a 2-bit output that comes as LSP, and the second bit. Then this AQN, and the first bit of AQN goes as clock signal to the second mod 4 counter, that is M2, and which gives an output of AQ32, that is second and third and fourth bit. And then AQN3, AQN fourth bit goes as clock signal to the third mod 4 counter, which gives the output as AQ 45, means the fifth and the sixth bit. So overall the output would be AQ 5 to 0. Means 2 bits will come from mod M1. The next, the higher 2 bits would come from M2, and the highest 2 bits will come from M3. This is the test bench for it. Module name mod 64 TB. Inputs are clock and reset. Output are defined as wires, and there are 6-bit outputs, AQ, AQN. Instantiation of the unit under test. Mod 64 is the module name mod 64, and it has used instantiation of 3 mod 4 counters, which had used instantiation of toggle flip-flops, and that had used instantiation of D flip-flop. So this mod 64 counter is instantiated. Initialize, then we will initialize the inputs as clock equal to 0, reset equal to 0. They will be put in begin in block. We will give a 100 nanosecond global reset time for. Then we will put stimulus here. Again, in initial begin in block, we will put, first of all, we will put a monitor command. Along with time, we will list out the variable names that are to be monitored, that is clock, reset, AQ, and AQN, which are the outputs. Clock and reset are inputs. And then after 1 nanosecond, reset is equal to 0. And that is 1 nanosecond from simulation time 0. Then again after 1 nanosecond, clock is 1, that is 2 nanosecond from simulation time 0. Again after 1 nanosecond, reset is equal to 1, that is 3 nanosecond from simulation time 0 up to here. We will end the block, and we will define a clock again. This clock is of time period 2, and we will end the module. We will run the simulation. So as it is a mod 64 counter, it would have 64 different states, starting from 0. At every positive edge of clock, the state will change. It will go to the next state. Starting from 0, it will go up to 0. It is here, 0. It will go up to 63. It is moving to the next state at every positive edge of clock, and it went up to, we'll scroll it and see, it went up to 63. And again, after 64th state, that is 63, is reached, it will again start from 0. After 63, it will go to 0 and again start and go up to 63. This is the output. AQ and clock and reset are the inputs. AQ, AQN are the outputs. So there is a simulation for mod 64 counter, which has 64 different states. Then we will move on to the next example, which will signify the importance of blocking and non-blocking statements. We will be demonstrating that using 4 different examples. And for swapping of bits, we will check how blocking or non-blocking helps in swapping. First example. This is code 1. We have 4 different codes. We will try 4 different codes, 2 with blocking statements, which have immediate assignment, and the next 2 with non-blocking assignments, which have delayed assignment and immediate evaluation. We don't have a test bench for it. We can note that we don't have a test bench for it. We are not defining any. Defining any source code. We are directly defining registers here is a code with variable name code which is of 16-bit, which will be a 16-bit input. This input will be hexadecimal form. As you can see here, code is equal to ABCD, which is the 16-bit hexadecimal input data. We don't have any source code here, so directly in the test bench format, you can see we will be checking whether the data swaps are a bit swap or not. So this reg, the reg is a 16-bit input code. Then next is clock, CL clock. Initial begin, we will initialize code equal to 0, clock equal to 0, end it always. We will define a clock with time period 200 nanosecond. Then at every positive edge of clock, we will begin the execution of this begin block. Here, code 8 to 15. 8 to 15 means this the higher 8 bits of the data, which is AB, is immediately assigned to code 0 to 7, which are lower 8 bits of data input, and that is CD. And using this blocking statement. So basically, code 0 to 7 now contains AB, and code 8 to 15 is still intact. It is AB only. Then in the next immediate assignment and blocking statement, code 15 to 8, which was AB, is assigned code 0 to 7, which again is AB. So the output should be AB, that we will check through simulation. So AB. That is, we couldn't swap the bits using this immediate assignment or blocking statement. We will go for code type 2 and see whether we are able to swap again using these immediate assignment blocking statements only. So we will close it and go to code type 2. It's updating. This is code type 2. Again, it is similar. Everything reg is there, 16-bit data input is there, clock initial begin. Again, we will initialize the code and clock equal to 0. We'll define a clock. Only thing is this order in which we had written in the previous example, we had written code 70 at left hand side, and this code 8 to 15 was on the right hand side. So this order has changed. Just the order has changed, but still we are using immediate assignment and blocking statement. So data is the same as the previous example, that is ABCD, 16-bit hexadecimal input ABCD. What happens here, we can see that code 0 to 7. Code 0 to 7 is what? It is CD. Is immediately assigned to code 8 to 15. Code 8 to 15 was AB, and it has become CD now. Then again, code 8 to 15, which is it is immediate assignment using a blocking statement, as code 8 to 15 has now become CD. It is getting assigned back to CD, which is already CD. So this initial begin, this is what the data was, means hashtag 100, a code equal to ABCD. Based on this data, I was trying to explain this assignment. And display and monitor, we will see what the actual output is, whether the bits swapped or not. See, it is CD. We couldn't swap the bits. Means expected was CD AB, but we are getting CD. In the using immediate assignment blocking statements, in both the examples we couldn't swap. Just got repetition of bits. CD. Earlier it was AB. So we'll go for the next example, which is using immediate evaluation and delayed assignment. That is non-blocking. That is a non-blocking case. This code 3. Similarly, reg is a code of 16 bits. All the things are similar. Reg, clock, initial begin for initialization, then defining a clock using always block. Then always at the rate of positive edge of clock, we will begin in this execution. We will begin execution of these statements using non-blocking late assignment. That is, means assignment will be late, but evaluation will be done at the same instant. So code 70 is evaluated and it has to go to code 8 to 15, but it is not assigned yet. So, and then code 8 to 15, which is AB, has to go to code 7 to 0. It is evaluated, but it has not gone yet or not assigned yet. So this initial begin hashtag 100 code means this is the code input that we are providing. So when this beginning block closes, then only assignment happens. Assignment takes place. So what happens is code 7 to 0 after this beginning block closes will go to code 7 to 7 to 0, which was CD, will go to 8 to 15. So and code 8 to 15, which was AB, will go at the place where CD was. So output should be CDAB that we can check through simulation. So CDAB or ABCD, we are getting CDAB. That is, swapping is occurring here. Similarly, we will check for another case. That is example 4. Updating code 4. It is similar. Reg is a 16-bit input code. Reg is a clock then, and initial begin, initializing a code and clock, and defining a clock using always block. Then always at the rate of positive, which of clock we will begin in. So this just the order has changed. There we had code 70 on the right hand side, and here we have it on the left hand side. So this order, just the order has changed. Still we are using non-blocking statements. So evaluation will be at the same instant, but assignment will not happen. Assignment will happen later on together. So this initial begin hashtag 100 code 16H ABCD. This is the input. So code 8 to 15 has to go to codes 0 to 7. That is, code 8 to 15 is AB. It has to go to the place of CD, and code 0 to 7, that is CD, has to go to the place of code 8 to 15, which is AB. So during it is evaluated but not assigned. After the beginning block closes, it will be assigned. CD will come at the place of AB, and AB will go to the place of CD. So this will be displayed on monitor, and we can check what the output is. It is CDAB, it is swap. So thus we could highlight how using non-blocking statements we could perform this simple task called data swapping, which was not possible through blocking statements at all. Means whatever we tried, we couldn't do. We couldn't achieve data swapping. So thus we end the simulation part of demonstration 2, where we covered the simulation of some of the sequential circuits that were taught in the lectures. Thank you.